You see where that arrow is?
Sorry, am I muted or?
Okay, put it to your headphone. You hear him?
I don't think he's muted. Can you not hear anyone?
Sorry, are you talking to me? Okay. Anyways, so as I was saying, I'm just going to be using Python to teach this workshop, but you can use any language or any editor you prefer. And even for the challenges, you're allowed to use any language. So you don't necessarily have to use Python. Now, there's this Zoom top bar that's blocking the tabs. So I kind of want to move it, but it doesn't look like I can do that. So, oh, never mind, I can do that. Okay. So as you go and download Python if you want, so you can just click on this link. You guys all have the link to this Google Doc, right?
Could you send the link in chat just in case people don't have it?
I'll do that right now. The one with the link. This should be correct. Yeah, okay. Okay, so you can go ahead and download Python if you want. And once you download Python, you will also have idle. So if you just go into your Windows bar and search idle, that'll give you an editor that comes with Python. And so as you're doing that, I'm just going to briefly go over today's schedule. So from 1:30, which is around now, so from 1:30 to 2:30, we'll be going over recursion and introduction to graphs. And so that's algorithms 1. And then after at around 2:30, you're going to go on a break and you'll go to Discord where Lily is going to host a Kahoot. And so you'll have a break and a small activity until 3. And after that, it'll be algorithms 2, and that'll run for another hour. So that's from 3 to 4. We're going to look at some graph algorithms like a depth first search and breadth first search. And after that, there's going to be another 30-minute break. And I'm going to assign another exercise, and you're going to work on that for half an hour. And then after that, I'm going to take up that exercise in algorithms 3. So that is the plan for today. Okay, so before I begin, if you ever just have any question, feel free to unmute your mic or type something in the chat and to ask questions. And if you need me to slow down, you can also tell me that. And yeah, I'll just get right into it. So first thing we're going to look at is recursion. But before we can talk about recursion, let's first review what is a function. So a function is a piece of code that takes in some number of arguments, satisfying the parameters, and which is possibly none, because you can also take in no arguments from a function, and it'll return an output. And sometimes a function won't return any output. And we assign a name to this set of instructions, so we can call this function in our program, and that piece of code will execute before the rest of the program begins. So since I'm sharing my application here, I'm just going to use like an online instead of idle. So let's look at an example of a function in Python. So this is what this function looks like. So this is functions in Python are all going to look something like this. So we're going to type def space, and then you're going to type the name of the function. And so you put your name function and then brackets, and then inside here you're going to have parameters. So this is a parameter 1, 2, and etc. So you can have 0 parameters, and you can have more than 1 parameter. And you type colon, and that'll bring you to the next line, which is hopefully indented. And then there you're going to write the definition of the function. And so you're going to maybe do something arguments, and then you're going to return some result. So this is what a function will generally look like in Python. And so if we compare that to what we have here, so df, and this is going to be the keyword that defines a function. And so the name of our function is square. And so that's the name that we're going to use to call the function. And x is the input parameter. So whenever you call this function, you're going to pass in some inputs. And this is also called an argument. This is what you're passing into the function. And it takes this x, and this is just a comment. So in case you've never used Python before, whenever there's this pound symbol, that means that whatever is after it is just ignored. And so this is just to make the code more readable. And then after that, simply, we're just going to return x times x within the function, and that should hopefully square any number. And so everything I'm explaining right here should be in the doc if you just scroll down. So I'm talking about the properties of functions right now. So we use df as the keyword to define a function. So unlike some other languages, there's no need to specify the return type. So for example, in Java or C++, you might need to specify you're returning an integer or returning nothing, but in Python, you don't have to. And we use return to return the result of the program. And it's very important that return is not the same as print. So the output of the function won't be outputted to the console and only to the program that called the function. So for example, if I run this piece of code right now, you'll see that even though I called square 3, so should output 3 squared, which is 9, but it's only outputting to the program, right? So it's almost like I just put a random 9 in the program and did nothing with it. Now, if I wanted to output square at 3, I would have to print it out. So outputting from the function is not the same as outputting it to the console. So you can see when I put print square 3, it's going to output the value. So that'll give me 9. Okay, so return will also terminate the function. So let me show a brief example of that. So if I have a function, let's just call it f, and it takes in no parameters. And I'm going to say, if I say return something like 10, and then I'm going to try to do something like print hello world, then I go ahead and print f. What's going to happen there is it's going to print 10, but it never executed this command. And that's because return already terminated the function before it reached this point. And so anything after the return statement is called is going to be ignored. And so I instead put this before the return statement. You can see that I'm printing hello world and then 10, right? So that's just how return works. Okay, and I already mentioned this. So square is the name of the function, and we're going to use this to execute a piece of code. So whenever I want to call this function, I'm taking the name and then I'm executing this piece of code. So when I say square 3, it's going to run this function, and then it's going to come back and give me the value. And the program is going to resume running. Okay, and x is called the function parameter, and the function will use x when referring to the input argument. So in this case, when I pass in 3 to the function, x is equal to 3. So 3 times 3 is 9. When I pass in -7 to the function, x is equal to -7. And so -7 times -7 is 49. And so, yeah, those are just the parameters. And calls the function must satisfy the parameters in the definition. So if I specify that there has to be just one number there, then I can't put something like 2 numbers. So if I say 3, 7, it's going to tell me that it takes 1 positional argument, but 2 were given. And you also obviously can't put nothing there because it's missing 1 required positional argument because we specified there has to be something there. And so that's what a parameter means. Okay, and 3 and -7 are arguments passed into the function. So this is just terminology. 3 and -7. Those are the things we're putting into the function, and so we call those arguments. And you can't call a function before defining it. And okay, I can just demonstrate this. So if I try to call square or -2 before this function's definition, and I run it, what happens is it says name square is not defined. And so you might say, hey, it's defined right here. Why wouldn't it be able to recognize what square is? But just recognize that if this is called before this is defined, then the interpreter won't know what square means. So you can call this function, of course, after. So if you call it afterwards, it's not going to give you any error. Okay, so far, are there any questions about functions in Python? Okay, and if you have any questions at any point, you can just either type in the chat or unmute and ask the question. Yeah. So now that we know what a function is, what is recursion? So recursion is when something is defined in terms of itself. So in computer science, a recursive function is a function that calls itself in its definition. So we're going to look at a classic example of recursion, and that's the Fibonacci sequence. So here I'm going to define the sequence as follows. So for some non-negative integer n, if n is equal to 0, then I'm defining fib at 0 to be 0. And if n is equal to 1, I'm defining fib at 1 is equal to 1. And otherwise, I'm defining fib at n is equal to fib at n minus 1 plus fib at n minus 2. So this is a mouthful, but in other words, the 0th term is 0, the first term is 1, and all the terms afterwards are defined as the sum of the previous two terms. So let's look at the sequence here. So this is the sequence. You can see that the 0th term is 0. So in computer science, we zero index things. So that's why I decided to zero index the sequence as well. So the 0th term is 0, and the first term is 1. And when we add 0 and 1, we get 1. And we add 1 and 1, we get 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And hopefully you see what's going on here. So let's look at the implementation of this in Python. So this is implemented exactly as how I defined it right here, right? So if n is equal to 0, fib at 0 is equal to 0. So I have this function called fib, and if n is equal to 0, I'm returning the value of 0. And if n is equal to 1, I'm returning the value of 1. And now, why don't I have to put something like else if and else? And that's because, as we said before, return will terminate the function, right? So if n is equal to 0 and I return the value of 0, the rest of the program won't run. And similar case with 1. And so it's enough to just put if statements there. Okay, and so after these two cases, we're defining any other fib at n to be fib at n minus 1 plus fib at n minus 2. And this is where we're calling the function in its own definition. This is what recursion is, right? So this is the name of the function. And after this first line, the rest of this is the definition. So in this definition here, we are calling the function again. And so this is what a recursive function is. So we're defining fib at n, and we're calling fib at n minus 1 plus fib at n minus 2. And let's run this function and see what it outputs. So I'm running fib at 4. I'm printing fib at 4, and it's giving me 3. And let's just go and check our sequence. So 0, 1, 2, 3, 4. So 4 should be 3. And that's correct. Okay, so what actually happened in this call? So I know it says f here, just pretend that it says fib, I guess. So we're calling fib at 4, right? So fib at 4, let's see what happens. So when we call fib at 4, 4 is the argument, and n is going to be assigned to be equal to 4, right? So if n is 4, first of all, we check if 4 is 0, so 4 is not 0. Is 4 1? No. Then we're going to return fib at 4 minus 1, which is fib at 3, and fib at 4 minus 2, which is 2. So when we call fib at 4, okay. So just to make sure, can you guys all see the drawings, the green drawings? I don't know if.
Yeah, we can see it.
Yeah, we can.
Okay. So this is where we're calling fib at 4. So in fib at 4, we said, okay, it's not equal to 0. 4 is not equal to 0. 4 is not equal to 1. And now it's saying, okay, call fib at 4 minus 1. So that's fib at 3. And so that's where we're calling this. So now we're here. So now we're calling fib at 3, and now n is equal to 3. So is 3 equal to 0? No. Is 3 equal to 1? No. So then call fib at 3 minus 1. So we're not worrying about the second one here yet, since we have to find out the value of the first one first. So fib at 3 minus 1, that's fib at 2. And so we're going down here. Okay, so now we're calling fib at 2. Is 2 equal to 0? No. Is 2 equal to 1? No. So then we return fib at 2 minus 1, and that's fib at 1. Right. So now that we have fib at 1, n is equal to 1. So is 1 equal to 0? No. Is 1 equal to 1? Yes. Right. So now we're returning 1. So what happened here is that it gave a value of 1 to fib at 2. And fib at 2 isn't done, right? It's not finished yet. Fib at 2 still has to complete the second argument here. So fib at 2 minus 2, that's fib at 0. And so fib at 0 is 0 equal to 0? Yes. So return 0. And so it went down here, and since we confirmed that 0 is 0, it returns the value of 0. And what did we say to do with these calls? Well, we're going to add them up, and it's defined as the sum of the previous two terms. And so 1 plus 0 gives us 1. So fib at 2 should be 1. And if you want to check our sequence, I guess I can't scroll when I have the school open. But if you check the sequence, the second term, so 0, 1, 2, the second term should be 1. Okay, so now fib at 3 isn't done yet either, right? So fib at 3 still has the second argument, or the second call here. So that says fib at 3 minus 2. So that'll give us 3 minus 2 equals 1. So fib at 1, we know that that's equal to 1, so it'll return 1. So the 1, it's going to return 1 to 2, or sorry, return 1 to fib at 3. And now that we have the 1 and the 1, we can add them up to get 2. And for this tree, since I'm doing it manually, I'm not going to go through like the same process with this tree. You just know that fib at 1 is going to return the 1 to fib at 2. It's the exact same process, this one and this one, right? You can see these are the exact same thing. And there's actually ways you can optimize the recursion using these overlapping subproblems, but we're not going to get into that today. And since I'm doing it manually, you know that fib at 0 is going to return the 0, fib at 1 is going to return the 1, and fib at 2 will have a value of 1. And finally, now that we have all our calls, you know that 1 plus 2 is going to give us 3. And so that's what happened in this program, right? So that's how we found the output of fib at 4. Okay, does anyone have any questions about recursion calls?
And before we get into the next topic, I sent the workshop code into the chat. What that is basically you get points at JumpStart for attending different workshops. So make sure to jot down the code right now. You can, if you're on the Discord, you can go to the bot channel, type in /code and put it in the workshop code, and you'll get points for attending this workshop. Or you can write it down and put in the code after the workshop. But please note that the code has an expiry date, like an expiry time. So after 10 minutes after this workshop ends, the code is going to be invalid. So yeah.
Okay, so if there are no questions, I'm just going to keep going and talk about general recursive functions. So properties of useful recursive functions. So in every useful recursive function, there must be some way for the recursion to stop. And in this example, we have something called base cases. And these base cases are when fib at 0, these base cases are fib at 0 is equal to 0 and fib at 1 is equal to 1. And so when either n is equal to 0 or n is equal to 1 it satisfies, we stop calling the function. So we're stopping the recursion. So let's look at the function again. So define fib at n. So if n is equal to 0, notice that in this case, we're not calling fib at n again, right? So this case is not technically recursive. So if n equals 0 is satisfied, we're simply just returning some value. And we're not calling the function again. The same thing with n is equal to 1. So if n is equal to 1, then we're simply returning a value of 1. We're not calling the function again. It's only if none of these two cases are satisfied that we're going to return values that require the calls of fib, right? And so these cases that don't require us to call the function again, these are what I'm referring as base cases. And so these base cases, essentially, they help us stop the recursion. And the second property is that the recursive function must be called in a way such that it approaches and eventually reaches the base cases or cases where the function stops calling itself. So in this case, we're always subtracting 1 or 2 from a positive number. So we can expect the base cases n equals 0 and n equals 1 to be reached. So if I input any positive integer here, we can see that we get a valid value, and seventh term should be 13. So 0, 1, 2, 3, 4, 5, 6, 7. So it should be 13. And that would be perfectly fine for this Fibonacci function. Now, we only defined it for non-negative integers for a reason, because if I put in something like fib at -5, and I run it, what it's going to say is give me an error, first of all, and it's going to say recursion error, maximum recursion depth exceeded in comparison. So what happened here? So let's try to trace this function a little bit. So if n is equal to -5, which was what was passed in, then -5 is not equal to 0. Okay, -5 is not equal to 1. Okay, so then we call -5 minus 1, so fib at -6 and fib at -7, right? So we're calling like fib at -6 plus fib at -7. And so you realize that this will just keep going. So fib at -6 will then be equal to fib at -7 plus fib at -8. And if it keeps going down to like -9, -10, -11, it's never going to reach 0 or 1, right? You just don't subtract numbers from negative numbers to get to 0 or 1. It's just not possible to stop the recursion in this case. So with Fibonacci numbers, in the case of Fibonacci numbers, we can only expect the base cases of 0 and 1 to be reached if we're inputting a non-negative integer. And so that's another property of recursive functions. So what happens if the recursion doesn't stop? It's going to give you a recursion error, as I just demonstrated. And if you get this error, it's probably because either you're calling the function incorrectly or you don't have a base case set up for functions. Okay, Okay, half an hour. So I'm going to show another case of a recursive function. So this one's also pretty classical. So it's going to implement the factorial function. So in case anyone is unfamiliar, n factorial is defined as 1 or n times n minus 1 times n minus 2 all the way to 3 times 2 times. So for example, 5 factorial would be equal to 5 times 4 times 3 times 2. And 3 factorial would be something like 3 times 2 times 1. So that's what a factorial function is. And if we were to implement the factorial function recursively, I'm going to name this function factorial. And it's going to take in one input, so that's going to be n. So in its definition, so first of all, you could, there's the case that 0 factorial is equal to 1, but let's just define it for positive integers. So if n is equal to 1, then I'm gonna say return 1. So, and that's because 1 factorial is equal to 1, right? So if n is equal to 1, then return the value of 1. Otherwise, and I could put an else in here, that there wouldn't be anything wrong with that. But it's not necessary, because if this case is satisfied, then it's going to return and terminate the function, right? As we talked about in the definition. So in this case, what we're returning is essentially realize that once we have the n factored out, all we're left with when we take n minus 1 times n minus 2 times ... 3 times 2 times 1, this is just n minus 1 factorial, right? So this is essentially n minus 1 factorial. And so what this means is that we can simplify this to simply n times factorial n minus 1. And so let's just call this function and see if this works. At 120. Okay, so confirming, so 2 times 3 is 6, 6 times 20 is 120, and so that would be correct. So what happened here? Okay, so it called factorial at 5. We checked if 5 was equal to 1. No, so then it would be 5 is equal to 5 times factorial. Right? Because 5 minus 1 is equal to 4. Right? So then it calls factorial at 4 now. So, okay, factorial at n. So is n equal to 1? Is 4 equal to 1? No. So then it calls 4 times factorial at 4 minus 1. So this becomes 5 times 4 times factorial. So going through the same process, 5 times 4 times. Now we need to evaluate factorial at 3. So is 3 equal to 1? No. So then we go to this statement and do n times. So in this case, n is equal to 3 times factorial at 2. And if we continue this process, eventually we reach the case of 2 times factorial at 1. And now at factorial at 1, what happens is it says is 1 equal to 1, and that's true. So what happens is it simply returns 1. Notice that in this base case, we are not calling the factorial function again, and so that's what makes this the base case. So that is equal to 5 times 4 times 3 times 2 times. And so that's the factorial function and how it's equivalent to that. Yeah, I guess, are there any questions? Okay, so what happens here is because we're first of all, we're subtracting from the input parameter, the input argument, and then we're testing it against the base case of n equals to 1. And we know that if we're calling it in a way that it doesn't reach the base cases, we'll reach infinite recursion. So, for example, if I type factorial at -7, then what I get is a recursion error, right? So maximum recursion to exceed it. So what happened here was I kept on subtracting from -7, so I get -8, -9, -10, -11, and so on. And this sequence here is never going to reach n is equal to 1, right? That this case will never be satisfied, and this recursion is going to go on forever. Okay. That will be the section for recursion. Again, if you have any questions at any time, feel free to type in the chat or just unmute. And now we're going to talk about graphs. So these things look very unrelated, but later on in the second hour, we're going to be using recursion again. So yeah, so let's now talk about graphs. So before we can start graph algorithms in the second hour, we're going to need to talk about some graph theory terminology and some definitions. And so this is kind of just preparation for the next hour. So that'll be algorithms 2. Okay, so first of all, what is a node? So you can think of a node as a location. Zoom out a little bit. So I'm going to draw, for example, this is kind of just an abstract location. I'm going to use this circle to represent a node. And you can think of a node as a location or intersection of edges. And nodes are also called vertices. Now, what is an edge? So you can think of an edge as a road connecting the locations. So these are the locations, and an edge connects the locations. So if I had 2 locations and a road connecting them, so this is the edge. So the edge is this, and these are the nodes. So the nodes are these. Right. So each edge connects 2 nodes. So here are 2 nodes, and this edge connecting them. And if the edge only goes one way from one node to the other, it's called a directed edge. And if the edge goes both ways, it's called an undirected edge. So if there are no arrows, then that usually indicates that it's undirected, so it goes both ways. So for simplicity, I'll name this node A and this node B. So if it goes from A to B and goes from B to A, then we call it an undirected edge. So you can think of this as a road on the street. So if it's a 2-way road, meaning the cars can go one way and the other way, so there's 2 ways of traffic, then it's undirected. But if I draw an arrow here and say, okay, so only A can go to B using this edge, and B can't go to A using this edge, then it's called directed edge. Yeah, so in this case, A would be able to visit B, but B won't be able to visit location A. So a graph is the network of nodes connected by edges. So a graph consists of a set of nodes and a set of edges. So I can have many more nodes. So a graph is definitely not limited to 2 nodes. I can have a lot of nodes, and I can have a lot of edges. So I can have an edge here, an edge here, an edge here, edges here, here. I can have more nodes. And so this entire thing we would call a graph. And a graph is called connected when there's at least one path between each pair of nodes. And this is the type of graph we'll be dealing with today. So this graph is not connected, right? Because if I look at let's just say these 2 nodes right here, there's no path in between them. So I can't get from one node here to another node here. And so these components, I would call them, are all separate, and there's no edge joining them. And that's why this graph right now is not connected. But if I were to draw edges between them, like so, and I say they're all undirected edges, and then this entire graph would be a connected graph. So you can kind of visualize that now all the nodes or all the locations are connected by roads. Okay, and a graph composed of directed edges is called a directed graph. So for example, I can have with a directed edge, another directed edge, another directed edge, and this would be a directed graph because all the edges are directed. And a graph with only undirected edges is called an undirected graph. So I can have another graph, and the edges go both ways. So I can just draw two arrows representing that. And so this would be an example of an undirected graph. And a weighted graph is a graph composed of edges that have an assigned weight. And we'll only be dealing with unweighted graphs. So sometimes when we deal with distances, we can say that one edge has a distance of maybe 7 and 5. But today we're not going to get into weighted graphs. Okay, and yeah, so a cycle. A cycle is a non-empty sequence of distinct edges, which joins a sequence of nodes starting and ending at the same node. So that's a little bit of mouthful, but you can kind of envision what a cycle is. So for example, if I can travel from, let's name this node 1, node 2, node 3, node 3. So a non-empty sequence of distinct edges. So this edge is distinct from this, is distinct from this. So this is a sequence of edges from 1 to 2 to 3 back to 1. And it joins a sequence of nodes. So that's 1, 2, and 3. And it starts and ends at the same node. So 1, 2, 3, 1. So for example, this would be an example of a cycle. And so with this, so if I label this 1, 2, and 3, and I go from 1 to 2 to 3 to 1, my edges are distinct. I have 3 edges, and my sequence of nodes is 1, 2, 3, 1, and it's starting and ending at the same node. So it's starting at 1, 1, 2, 3, 1, and it's going to end at 1. And so that's what a cycle is. Now, it doesn't have to be 3 nodes, and both, as I just demonstrated, both undirected graphs and directed graphs can have cycles. And I can draw maybe a cycle of 5 nodes. So that would go to here, that can go to here, that can go to here, that can go to here, and that can go to here. And that would be an example of a cycle as well. So if I label this 1, 2, 3, 4, 5, I can go from 1 to 2, 2 to 4, 4 to 3, 3 to 5, 5 to 1. So that would be another example of a cycle. Okay, neighbor. Node B is said to be a neighbor of node A if there's an edge connecting A to B such that A can go to B. So if I have A and this is a node and there's an edge going to B, and let's just say at first that this is a directed edge, so only A can go to B, then B is a neighbor of A, but A is not a neighbor of B because B can't go there, right? B can't use this edge unless there's another edge. B can't go to A. Now, what if there was another node C, right? So if I have a node C here and there's an edge from B to C, is C a neighbor of A? No. No, because in this graph, it's only a neighbor if there's an edge connecting A to B. So when we're talking about A to C, it's only when there's an edge connecting A to C that C is a neighbor of A. Now, even though A can go through B to C, I would still not call C a neighbor of A. Now, if there was an edge directly going over like this from A to C, then C would be a neighbor of A. And keep in mind that just because A is a neighbor of B doesn't mean that sorry, just because B is a neighbor of A doesn't mean that A is a neighbor of B, because our edges can be directed, right? So, but if these are all undirected, then they would all be neighbors with each other. It's getting a little crowded, so a path is a distinct sequence of edges joining a distinct sequence of vertices. So if I had a couple nodes here, I'm just going to draw some edges between them. Okay, so a path is a distinct sequence of edges connecting a distinct sequence of vertices. So I can go from here, from this node to this node, to this node, to this node, to this node, and that would be a valid path because these edges are all distinct and these vertices are all distinct, right? So that would be a path, and it has to be a sequence of vertices. You can't really like pick edges that are not really connected by vertices. That wouldn't make sense, because if you think about what a path means, it's kind of like a path going through the graph, right? So it has to be distinct edges and distinct vertices. And you can't have something like okay, I'm going to go from this vertex, I'm going to go from this node to this node, to this node, to this node, back to this node. And that's because we can't have the same vertex being visited in the same path. So a path means a distinct sequence of vertices. So this would be an example of a path, would be a non-example of a path because it's not visiting distinct vertices. Okay, so let's consider this graph right here. So we have 7 nodes in the graph, first of all, and they're numbered from 1 to 7. And today, when we're going to be programming graph theory, we're just going to label the nodes 1 to 7 for convenience. Okay. So there are 7 edges, so we can count them 1, 2, 3, 4, 5, 6, 7. And first one goes from 1 to 6, then from 6 to 5, and 5 to 2, 2 to 6, 3 to 7, 4 to 3, and 3 to 5. And we also know that this is a directed graph. So these arrows indicate the direction. Okay, and 6 to 5 to 2 to 6 is a cycle in the graph. So we can see that 6 can go to 5, 5 goes to 2, 2 goes to 6. So a couple of things, it's distinct edges. So these 3 edges are distinct from each other. And we're traveling through a sequence of nodes. And we're starting and ending at the same node. So 6 to 5 to 2 to 6. So we're starting and ending at 6. Okay, so the final thing before we go on break for activity is adjacency lists. So when we're implementing graph theory algorithms with code, we need a way to store the graph so we can access the nodes and its neighbors. So there are several ways to do this. For example, like adjacency matrices or edge lists. But today we're going to mainly focus on adjacency lists because they're the most useful to us. So an adjacency list is a list of lists used to represent the graph. And each entry in the adjacency list stores the neighbors of the node according to its index. So let's look at an example here. So you notice that ADJ is the name of the list, and this is the list, right? So everything here are the contents of the adjacency list. And within the list, I have lists. So it's a list of lists, right? So remember that in most programming languages, we have 0 indexed. So if we number our nodes from 1 to 7, then the 0 is just left blank because node 0 doesn't exist. So let's talk about node 1. So the neighbors of node 1. So who can node 1 visit directly? using an edge. And now the only node that node 1 can visit is 6, using one edge. So 6 is a neighbor of 1. And if we look at node 2, the only thing it can visit is node 6 as well. So the adjacency list only contains 6, or sorry, 6 right here. And if we look at node 3, it has 2 neighbors, can go to 5 or it can go to 7. So here the adjacency list is 5, 7 in some order. It doesn't have to be in a specific order when you're constructing the adjacency list, because it's just kind of like an unordered list of neighbors of the node. So similar idea, node 3 is a neighbor of node 4, so node 4 can visit node 3. Node 2 is a neighbor of node 5, so 5 can visit 2. And node 5 is a neighbor of 6, and 6 can visit 5. And finally, for 7, 7 has no one that it can visit, so its adjacency list is empty. So how we're going to use this is that if we want to know about the neighbors of node 3, I just type adj at 3. And actually, instead of doing that here, I'll just copy this thing over to, oh, I closed it. What's it called? So if I wanted to know about node 3, then I would type adj at 3. And if I run that, that gives me 5, 7. And what does 5, 7 represent? Well, if we go back to the graph, if we look at node 3, 5 and 7 are its neighbors. And so that's the core idea of adjacency lists. We need an efficient way to access the neighbors of the nodes. And so we store them in a list like this. And let's try another example. If we wanted to know about the neighbors of 6, we type adj at 6, run that, and we get 5. And we look at node 6 in our graph. 6's only neighbor is 5. Remember that 1 and 2 aren't neighbors of 6 because there's no edge going to it. It's 1 going towards 6 and 2 going towards 6, right? So the only outgoing edge from 6 is going to 5. And so that's why 5 is the only neighbor of 6. And this. And so for the rest of the time that you have, so that'll be around 7 minutes, I'm going to ask you to make an adjacency list either manually or try to come up with a program that represents the following undirected graph. So this graph right here. And if it makes it easier for you, especially if you're using code, here are the list of edges. And just a final note on adjacency list, when you're doing the graph theory challenge this week, you might want the nodes or the locations to have actual names, like, I don't know, like home, store, mall, or school, rather than these abstract numbers. So right now we're representing these locations just abstractly by using these numbers, numbered from 1 to however many nodes there are. But you can substitute these numbers with the location names in an adjacency dictionary instead of a list. So a dictionary is like a map-like or hash table-like object. So if you use Java, it's a hash table. If you use C++, that would be something like an unordered map. And if you're for any other languages, I'm not sure. And the way you use this adjacency dictionary is that the location names are going to be the keys. And the exact implementation of this, I'm going to leave as an exercise because, well, the challenge is meant to be a challenge. So just to illustrate what a dictionary is, if I define something, D is equal to this, and I say D at some string is equal to a list of 3, 4, 5. Actually, I can name this like. Then when I say print D at, then hopefully it should give me the list 3, 4, 5. So instead of having a list of lists, you can also have a dictionary of lists. And technically, if since these don't have to be ordered, you could also have a list of sets or a dictionary of sets, but the exact data structure is going to be up to you. And when you're using these actual names, which are probably going to be strings, I'm just mentioning here that dictionaries might be helpful for you. Okay, so go ahead and work on making an adjacency list. Now this graph has 12 nodes, so it might be a little bit big if you're doing it manually. So if once you get the hang of it, I'm not saying you have to do the whole thing. Just once you get the idea, just make sure you understand everything about adjacency lists before we go on in algorithms 2 to study more algorithms. So first of all, does anyone have any questions up until this point? Okay, I think I'll leave this meeting up until 2:30, and you can work on this little exercise here. And then after that, you will go to Discord, and there will be a Kahoot, I think. Okay, so if you have any questions during this meeting, like until 2:30, feel free to ask. Otherwise, I'll leave you guys to work on this. Okay, so it's now 2:30, and I'll end the meeting here. You guys can go to Discord, and I think there's going to be an activity hosted. Okay, so I will end the meeting here.